Welcome! In today's session, we're tackling problem number 1095, find in mountain array.
This is an interesting problem involving binary search and mountain arrays, which are special types of arrays. Let's break it down step by step and explore the solution together. In this problem, you are tasked with finding a specific target value within what is known as a mountain array. A mountain array is a special type of array that first increases strictly up to a peak value, and then decreases strictly after the peak.
However, you cannot directly access the array elements like you would with a normal array. Instead, you are provided with an interface called mountain array, which includes two key methods, get, index, and length. The get method allows you to retrieve the value at a specific index, while the length method provides the total number of elements in the array. Your goal is to implement a function that searches for the target value in this mountain array. If the target value exists, you should return its index, otherwise, return -1. Importantly, to solve the problem efficiently, you must minimize the number of calls to the mountain array.get method. The function you need to implement is called find in mountain array.
It takes two parameters, the integer target, representing the value you are searching for, and an instance of the mountain array interface, which allows you to interact with the mountain array.
For example, consider the input where the target is 3 and the mountain array is 1, 2, 3, 4, 5, 3, 1.
In this case, the target value 3 is found at index 2. Therefore, the output is 2. This example illustrates how the target can exist on the increasing slope of the mountain array. Now, let's consider a scenario where the target does not exist in the mountain array. For example, if the target is 3 and the mountain array is 0, 1, 2, 4, 2, 1, the value 3 is not present in the array. As a result, the output is -1. Similarly, in another example where the target is 4 and the mountain array is 1, 5, 2, the target value is not found, so the output is also -1. These examples demonstrate how your function should handle cases where the target is absent, regardless of whether the array is large or small. In this final part, let's review some important constraints and edge cases for this problem. The length of the mountain array will always be at least 3 and can go up to 10⁻⁴. Each element in the array is a unique integer, ranging from 0 to 10⁻⁹. The target value you are searching for will also be within this range. You should carefully handle edge cases, such as when the target is the peak element, when it lies on either the increasing or decreasing slope, or when the target does not exist at all. Additionally, consider arrays with the minimum size of 3 elements. By understanding these constraints and edge cases, you can design a solution that is both efficient and robust. To solve the find in mountain array problem, one approach we can consider is the brute force method. The idea here is straightforward. Since we can only access the array elements through the provided mountain array API, we start by performing a linear scan to identify the peak element, which is the largest value in the array. This can be done by comparing each element with its neighbors until we find the maximum. Once the peak is located, we can then search for the target value in two parts, first, by scanning through the increasing section to the left of the peak, and then by scanning through the decreasing section to the right of the peak. While this approach is simple and avoids using additional memory, it has some significant drawbacks. The time complexity is O(n), which can be quite slow for large arrays. Furthermore, it doesn't take advantage of the sorted structure of the mountain array, making it inefficient for the given constraints.
A more efficient alternative is the optimized approach using binary search.
This method divides the problem into 3 logical parts: finding the peak element, searching for the target in the increasing section, and then searching for the target in the decreasing section. A key observation here is that the left side of the mountain is sorted in ascending order, while the right side is sorted in descending order. This allows us to apply binary search, significantly reducing the number of operations. To begin, we locate the peak using binary search. At each step, we evaluate the slope of the mountain by comparing the current element with its neighbor. If the slope is increasing, we move right, otherwise, we move left. This process continues until we pinpoint the peak element. The time complexity for this step is O log n, making it far more efficient than the linear scan in the brute force approach. Once the peak has been identified, the next step is to search for the target value in the two halves of the mountain array.
Starting with the left side, which is sorted in ascending order, we perform a binary search. By repeatedly dividing the search space in half and comparing the middle element to the target, we can efficiently locate the target if it exists. Similarly, for the right side, we apply binary search again, but this time adjust the comparison logic to account for the descending order of the elements. This ensures that we can correctly navigate the decreasing sequence to find the target. Each of these searches has a time complexity of O log n, and since we perform 3 binary searches in total, the overall time complexity remains O log n. This method is not only faster than the brute force approach but also leverages the sorted structure of the mountain array optimally. The optimized approach using binary search is the chosen strategy for solving this problem due to its efficiency and scalability. By breaking the task into 3 distinct parts, finding the peak, searching the left side, and searching the right side, we minimize the number of operations and API calls, fully utilizing the sorted nature of the mountain array. While the brute force method is simpler to implement, it is far too slow for large datasets, making it unsuitable for competitive programming scenarios. In contrast, the binary search approach offers optimal performance with a time complexity of O log n, though it does require extra care in implementation. Overall, this strategy strikes the perfect balance between correctness and efficiency, making it the ideal solution for this problem within the given constraints. In this problem, we are working with a mountain array, an array that increases to a peak and then decreases. The goal is to find the index of a specific target value within this array. However, we can only interact with the array through the mountain array API, which provides methods to fetch the array's length and access individual elements. To solve this efficiently, we will break the process into 3 steps, starting with identifying the peak element. The intuition here is that the peak is the largest element in the array, and because the array increases up to the peak and then decreases, we can use binary search to locate it. We initialize 2 pointers, low at the start of the array and high at the end. By calculating the middle index, mid, we determine which half of the array to search next. If the value at mid is less than the value at mid plus 1, the peak must lie to the right, so we adjust low. Otherwise, it lies to the left, so we adjust high. Once the loop exits, both low and high converge on the peak index, setting us up for the next steps in the algorithm. After identifying the peak, we focus on the left side of the array, which is sorted in ascending order. This allows us to use a standard binary search to look for the target. We initialize low to the start of the array and high to the peak index, then repeatedly calculate the mid index. If the value at mid matches the target, we return the index. If the value is less than the target, it means the target lies to the right, so we adjust low. Otherwise, if the value is greater than the target, we adjust high to search the left side. If the target is not found by the time the loop ends, we move on to searching the decreasing part of the array. This step leverages the sorted nature of the left half for efficiency and ensures we don't miss the target if it's on this side of the peak. Now we search the decreasing part of the array, which is sorted in descending order. This requires a modified binary search. We set low to 1 index past the peak and high to the end of the array. The process remains similar: calculate the mid index and compare the value at mid with the target. If they match, we return the index. If the value at mid is greater than the target must be further to the right, so we increase low. If the value is less than the target, we decrease high to search the left side. This adjustment accounts for the descending order of this section. If the target is not found after finishing the search, we return -1, indicating that the target does not exist in the array. The key insight here is that by using binary search on both sides of the peak, we achieve an efficient solution. The peak finding step and the 2 binary searches each contribute a logarithmic time complexity, resulting in an overall complexity of O log n. The problem heavily relies on the mountain array API, which allows us to interact with the array while abstracting its internal structure. This API ensures we can access the array's length and individual elements as needed. To implement the solution, we use standard pointers like low, high, and mid for binary search, which are crucial for navigating the array efficiently. Regarding complexity, finding the peak takes O log n, because it involves binary search over the entire array. Searching the left half, which is sorted in ascending order, takes another O log n. Similarly, searching the right half, sorted in descending order, adds another O, log n. Since these steps are sequential, the total time complexity remains O, log n. This makes the algorithm highly efficient, even for large arrays, as we repeatedly reduce the search space by half in each step. Let's walk through an example to see the algorithm in action. Consider the mountain array 1, 2, 4, 5, 3, 1, and a target value of 3. First, we find the peak. Initially, low is 0 and high is 5, yielding a midpoint mid of 2. The value at index 2 is 4, which is less than the value at index 3, so the peak must be to the right, and we update low to 3. Recalculating the midpoint gives mid as 4. Here, the value at index 4 is 5, which is greater than the value at index 5, so we update high to 4. At this point, both low and high point to index 3, confirming the peak. Next, we search the left half, which is 1, 2, 4, 5. Binary search here reveals that the target 3 is not in this portion of the array. Finally, we search the right half, which is 3, 1. A binary search on this section finds the target at index 4. The output is 4, demonstrating how the algorithm efficiently narrows down the search space to locate the target. Here, we begin by defining the findInMountainArray method inside the solution class. This method takes the target value we are searching for in the mountain_RR object, which provides two essential methods, get, index, to retrieve the value at a specific index and length, to get the size of the array. Within this method, we also define a helper function called binary_search. This function will perform a binary search between the given left and right boundaries to locate the target value. The is_ascending parameter helps us determine whether the current portion of the array is sorted in ascending or descending order. Inside the binary search, we calculate the middle index and retrieve its value using mountain_rr.get mid. If the middle value matches the target, we return the index. Otherwise, depending on whether the subarray is ascending or descending, we adjust the search boundaries accordingly. If the target is not found within the given range, the function returns -1. After defining the binary search, we calculate the length of the mountain array and initialize the boundaries left and right to encompass the entire array. We then enter a loop to identify the peak of the mountain array. The peak is the index where the array value switches from increasing to decreasing. To locate this peak, we calculate the middle index and compare its value to the next element. If the value at the middle index is less than the value at the next index, it means we are still in the ascending part of the mountain. In this case, we shift the left boundary to mid +1. Otherwise, if the value at the middle index is greater than or equal to the next value, it indicates that we could be at the peak or in the descending part. Here, we adjust the right boundary to mid. Once the loop exits, the left pointer will have converged on the peak index, which we store in the peak variable. With the peak identified, we now proceed to search for the target value in two stages. First, we perform a binary search on the ascending portion of the array, from index 0 to the peak. If the target is found in this range, we return its index immediately. If not, we move on to the descending portion, conducting a binary search from peak +1 to the end of the array. This time, we set is_ascending to false since the values in this range are sorted in descending order. If the target is found here, we return its index. If neither search finds the target, the method ultimately returns -1, indicating that the target is not present in the mountain array. Here, we define the mountain array interface, which provides two methods, get, to retrieve the value at a specific index, and length, to get the number of elements in the array. Next, we begin implementing our solution. The method findInMountainArray takes the target value we're searching for and the mountain array instance as inputs. Inside this method, we define a helper function called binarySearch. This function takes several parameters, the left and right boundaries of the search range, the target value, the mountain array instance, and a Boolean flag is ascending to indicate whether we are searching in the ascending or descending section of the mountain array. The binary search process begins with a while loop that continues as long as the left index is less than or equal to the right index. We calculate the midpoint within the current range and retrieve the value at that index using mountain_arr.get. If the midpoint value matches the target, we return the index. If not, we adjust our search range based on whether the array section is ascending or descending.
For ascending sections, we move the left boundary up if the mid value is less than the target or move the right boundary down otherwise.
For descending sections, the process is reversed.
If the mid value is greater than the target, we move the left boundary up, otherwise, we move the right boundary down. If the target is not found in the current range, the binary search function returns -1. Now, we move forward to find the peak element in the mountain array, which is the largest element where the values increase up to the peak and decrease afterward.
We use a modified binary search to efficiently locate the peak.
Starting with the entire range of the array, we calculate the midpoint and compare the value at mid with the value at mid plus 1. If the value at mid is less than the next value, it means we are in the ascending part of the array, so we shift the left boundary up. Otherwise, we are in the descending part, so we move the right boundary down.
Once the left and right pointers converge, we have found the peak index.
After finding the peak, we perform a binary search in the ascending part of the array, from index 0 to the peak index.
If the target is found, its index is returned immediately. If the target is not found in the ascending section, we proceed to search in the descending part of the array.
This is done by calling the same binary search function, but this time with the range starting just after the peak and extending to the end of the array.
The isAscending flag is set to false for this call to indicate that we are now searching in the descending section.
If the target is found in this range, its index is returned. If the target is not found in either section, the function ultimately returns -1, indicating that the target does not exist in the mountain array. This approach ensures that we efficiently search the mountain array with a time complexity of O log n, making it well suited for large arrays.
To solve the problem, the first step is to identify the peak of the mountain array. The peak is the index where the value is greater than its neighbors.
We initialize the search with left set to 0 and right set to the last index of the array, which is 5 in this example. The midpoint is calculated as 0 plus 5 / 2 equals 2.
At index 2, the value is 3, and at index 3, the value is 5. Since 3 is less than 5, it means the peak lies in the right half, so we update left to mid plus 1, which is 3. Next, we calculate a new midpoint as 3 plus 5 / 2 equals 4. At index 4, the value is 3, and at index 5, the value is 0. Since 3 is greater than 0, the peak must be to the left, so we update right to mid, which is 4. Finally, we calculate the midpoint again as 3 plus 4 / 2 equals 3. At index 3, the value is 5, and at index 4, the value is 3. Since 5 is greater than 3, we update right to mid, which is 3. Now, left and right both point to index 3, and we have found the peak at index 3, with a value of 5. Once the peak is found, the next step is to search for the target in the ascending part of the array. Here, the range for binary search is from index 0 to the peak index, which is 3. The first midpoint is calculated as 0 plus 3 / 2 equals 1. At index 1, the value is 2, which is less than the target value of 3. So, we update left to mid plus 1, which is 2. The new midpoint is 2 plus 3 / 2 equals 2. At index 2, the value is 3, which matches the target. Thus, the target is found at index 2, and the result is 2. In this example, the target is found in the descending part of the mountain array. The input array is 1, 2, 3, 4, 3, 1, 0, and the target is 0. As before, we start by finding the peak. We initialize left to 0 and right to 6, the last index of the array. The first midpoint is 0 plus 6 / 2 equals 3. At index 3, the value is 4, and at index 4, the value is 3. Since 4 is greater than 3, the peak lies in the left half, so we update right to mid, which is 3. The next midpoint is 0 plus 3 / 2 equals 1. At index 1, the value is 2, and at index 2, the value is 3. Since 2 is less than 3, the peak lies in the right half, so we update left to mid plus 1, which is 2. The next midpoint is 2 plus 3 / 2 equals 2. At index 2, the value is 3, and at index 3, the value is 4. Since 3 is less than 4, we update left to mid plus 1, which is 3. Now, left and right both point to index 3, and the peak is found at index 3, with a value of 4. After finding the peak, we proceed to search for the target in the descending part of the array. The descending section starts from index 4 and ends at index 6. The first midpoint is calculated as 4 plus 6, // 2 equals 5. At index 5, the value is 1, which is greater than the target value of 0. So, we move the search to the right half by updating left to mid plus 1, which is 6. The next midpoint is 6 plus 6, // 2 equals 6. At index 6, the value is 0, which matches the target. Thus, the target is found at index 6, and the result is 6. In this example, the target value is not present in the mountain array. The input array is 1, 3, 6, 7, 5, 2, and the target is 10. As usual, we start by locating the peak. We initialize left to 0 and right to 5. The first midpoint is 0 plus 5, // 2 equals 2. At index 2, the value is 6, and at index 3, the value is 7. Since 6 is less than 7, the peak lies in the right half, so we update left to mid plus 1, which is 3. The next midpoint is 3 plus 5, // 2 equals 4. At index 4, the value is 5, and at index 5, the value is 2. Since 5 is greater than 2, the peak lies in the left half, so we update right to mid, which is 4. The next midpoint is 3 plus 4, // 2 equals 3. At index 3, the value is 7, and at index 4, the value is 5. Since 7 is greater than 5, we update right to mid, which is 3. Now, left and right both point to index 3, and the peak is found at index 3, with a value of 7. Once the peak is identified, we first search for the target in the ascending part of the array, which spans from index 0 to the peak index 3. The initial midpoint is 0 plus 3, // 2 equals 1. At index 1, the value is 3, which is less than the target value of 10. So, we update left to mid plus 1, which is 2. The next midpoint is 2 plus 3, // 2 equals 2. At index 2, the value is 6, which is also less than 10. We update left to mid plus 1, which is 3. The next midpoint is 3 plus 3, // 2 equals 3. At index 3, the value is 7, which is still less than 10. We update left to mid plus 1, which is 4. Since left is now greater than right, the target is not found in the ascending part. Next, we search in the descending part of the array, which spans from index 4 to 5. The initial midpoint is 4 plus 5, // 2 equals 4. At index 4, the value is 5, which is less than 10. So, we update right to mid 1, which is 3. Since left is now greater than right, the target is not found in the descending part either. As a result, the output is -1. To analyze the time complexity of this algorithm, we can break it into 3 main steps. First, we find the peak element using binary search. In this step, the search space is halved on each iteration, making it efficient with a time complexity of O log n, where n is the length of the mountain array. Next, we perform a binary search on the ascending part of the array, which is the portion from index 0 to the peak. This step also has a time complexity of O log n, because the binary search algorithm continues to have the search space. Finally, if the target is not found on the ascending side, a similar binary search is carried out on the descending part of the array, specifically from the peak index plus 1 to the last index. Again, this step achieves O log n time. Since these 3 binary searches operate independently, the overall time complexity of the algorithm is the sum of these steps. Adding the time complexities of the 3 steps, we get O log n plus O log n plus O log n, which simplifies to O log n. Now, let's discuss the space complexity. The algorithm's space complexity is determined by the additional memory used. In the binary search function, only a constant amount of memory is required for pointers like left, right, and mid, as well as temporary variables such as mid_val. Similarly, the step to find the peak also involves just a few pointers and calculations, which means the space complexity for this step is also O1.
Overall, the algorithm does not rely on any additional data structures and uses only the input array and a small number of variables. Therefore, the total space complexity is O(1). This makes the solution not only time efficient but also space efficient. Now, let's examine the best, average, and worst case scenarios for this algorithm. In the best case, the target happens to be the peak element itself. Here, the algorithm needs only the peak finding step, which takes O log n, and no further searches are required in the ascending or descending parts. For the average case, the target is typically found during either the binary search on the ascending part or the descending part. The time complexity in this scenario remains O log n, as it is dominated by one or two binary searches. In the worst case, the algorithm has to perform all three steps: finding the peak, searching the ascending part, and then searching the descending part. Even in this case, the total time complexity remains O log n, as each step is logarithmic. This consistency in time complexity across all cases demonstrates the efficiency of the approach. Finally, let's compare this optimized solution to a brute force approach. A naive method would involve scanning the entire mountain array sequentially to search for the target. This linear scan has a time complexity of O(n), which can become extremely slow as the size of the array grows. In contrast, the optimized solution uses binary search to reduce the search space logarithmically, achieving a much faster time complexity of O log n. To understand why binary search is so efficient, consider its mathematical foundation. In each iteration, the search space is halved, and the number of iterations required to reduce n elements to a single element is proportional to log_2 n. Additionally, the constant overhead for operations like comparisons and arithmetic is negligible compared to the logarithmic growth. As a result, the optimized solution consistently achieves O log n time complexity, making it significantly better than the brute force approach for large inputs. When solving this problem, it's important to avoid some common mistakes that can make your solution inefficient or incorrect. First, not leveraging the mountain property of the array is a frequent issue. This problem isn't just a generic binary search. The mountain structure allows us to break the search into two distinct phases, ascending and descending, which simplifies the process. Searching the entire array linearly or treating it like a standard binary search leads to unnecessary complexity. Another mistake is implementing binary search incorrectly. Errors like miscalculating the midpoint or failing to properly adjust the low and high bounds, such as using low equals mid plus 1 or high equals mid 1 inappropriately, can cause infinite loops or off by 1 errors that break the algorithm. Additionally, failing to handle edge cases can lead to missed scenarios during testing. For example, you need to account for cases where the target isn't in the array, when the target is at the peak or at one of the boundaries, or when the array has only one or two elements. Finally, inefficient use of the mountain array API is another pitfall. Repeatedly querying the same index without caching results not only wastes time but can also lead to exceeding the API call limit, which is a constraint to keep in mind. Efficient caching is crucial for maintaining performance here. Another mistake to watch for is not verifying the peak index properly. Assuming the peak is always in the middle of the array without checking the mountain property can lead to errors, especially if the input doesn't follow the expected structure. Beyond avoiding common mistakes, there are key insights that can help you succeed in interviews. First, this problem and many of its variations benefits greatly from a divide-and-conquer approach, where you split the array into logical segments, such as the left side up to the peak and the right side after the peak. Understanding how to adapt binary search to handle these segments is a critical skill. Additionally, be mindful of API constraints. When you're asked to interact with a specific interface, such as the Mountain Array API, you need to work efficiently to stay within the given limits. Edge case handling is another crucial point. Always clarify edge cases with your interviewer, such as arrays that are only ascending or descending, or inputs of unusual sizes. Finally, time complexity often plays a big role in how solutions are evaluated. You should aim for an O log n solution, as the sorted-like structure of the mountain array makes logarithmic approaches, like binary search, the most appropriate choice. To further practice and master these concepts, it's helpful to explore related problems. For example, LeetCode 852, Peak Index in a Mountain Array, focuses on finding the peak of the mountain efficiently.
LeetCode 162, Find Peak Element, is another variation that deals with finding local peaks in an array.
Of course, LeetCode 1095, Find and Mount an Array, is directly related to the problem we're discussing. Additionally, LeetCode 33, Search and Rotated Sorted Array, involves a similar binary search pattern and is a great way to strengthen your understanding of these techniques. Now, in terms of alternative approaches, you might consider a single binary search that combines the peak search with the target search. While this method eliminates the need for two separate phases, it can become complex and harder to manage, so proceed cautiously.
Another option is a two-pass linear search, which involves first finding the peak and then searching for the target in the two segments. While this approach is less efficient at O(n), it's simpler to implement and can be a good starting point for beginners. Lastly, memoization is an excellent optimization technique in this context.
By caching the results of API calls for indices that you've already queried, you can avoid redundant computations and ensure that you stay within the API call limits, making your solution both faster and more reliable.
Great job! To recap, we used binary search and took advantage of the mountain array structure to solve this problem efficiently. Remember, practicing problems like these helps strengthen your algorithmic thinking. Thanks for joining, and we'll see you in the next session. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!